Here we make observations of a 3D engagement example. First, we define our inertial coordinate system with enumerated coordinate directions. We'll call them downrange, cross-range, and altitude respectively. The target is initially at the same altitude as the pursuer at 40,000 feet of cross-range. And the pursuer velocity is initially headed directly along the cross-range direction. The target velocity has downrange and vertical component. Here are the initial conditions for the pursuer and target. This term in the target velocity will be explained shortly. This is target acceleration magnitude and a frequency term that's defining a target maneuver. In this simulation, we include a first-order pseudo-pilot in the loop. It's just a first-order low-pass filter in each coordinate channel. Also, when the acceleration is commanded by the pronav law, it's limited to a magnitude of 30 degrees in any coordinate direction. We implement the zero effort miss form of the pronav law that was described in previous sections. And to compute an intercept final time, we have closing velocity and initial cross range. So the time it takes for the pursuer and target to occupy the same cross range position is used for the final time, or the time of intercept, throughout the simulations in this module. In this example, the target performs a weave maneuver. In the downrange and vertical direction, we have this time-dependent acceleration profile where the parameters are the target acceleration magnitude and a frequency of the weave. In the cross-range direction, there is no maneuver. It's just zero. So the pursuer and target approach each other with constant closing velocity throughout the simulation until the time of intercept. Integrating the acceleration, we get target velocity, and then setting time equal to 0, we obtain our initial conditions, which were in the previous slide. And we have 3 radians per second for the weave frequency and 6 g's of acceleration magnitude of the target. Integrating the target kinematics alone produces a spiral where the maneuver is in the altitude and downrange direction, and the cross-range direction just has a constant velocity. So this block diagram captures what we're going to simulate. We have the kinematics that were described in the previous module. There is no seeker model in this. Instead, we're taking the kinematics and directly computing time to go and zero effort miss normal to the line of sight. That produces our pursuer acceleration command in 3 dimensions. There's 1 component per coordinate direction in the inertial coordinate system. And then that acceleration command is G limited. That acceleration command that's G limited then goes into the pseudo-pilot, which is essentially a low-pass filter, and the achieved pursuer acceleration is then fed back into the kinematics. This process continues until TF, or the time to intercept, and the miss distance is recorded. So the following results were obtained with a 4th order ODE solver using adaptive time stepping to meet relative and absolute error tolerances of 1/10,000th. This is for a navigation gain of 3 and a time constant of 1 second. Some interesting behavior now in 3 dimensions. The pursuer responding to the spiraling behavior of the target with its own spiraling behavior as it attempts to achieve a collision triangle. If we look at this from different perspectives, we can see the oscillation in the pursuer response. In the vertical plane, the pursuer increases its altitude to the mean altitude of the target and begins to respond greater to target maneuvers as time approaches TF, or time to go 0. In the lateral plane, again, oscillation of increasing magnitude as T approaches TF, Finally, altitude versus downrange. We see the spiraling behavior of the pursuer as it responds to the target in order to establish the collision triangle. These are plots of relative position versus time in each coordinate direction. You can also think of this as range to the target resolved in each coordinate direction as a function of time. Now the target maneuver is in the downrange and altitude directions, and this is where we see the fluctuations in the range. In the center is the cross range. Since there's no maneuver in the cross range direction by the target, there is no interesting behavior in cross range as a function of time. It's simply a linearly decreasing line according to the closing velocity of the engagement. Looking more closely at the downrange, at the final time, the downrange miss is 11.8 feet. The cross-range miss, less than a foot. And the altitude miss, minus 21.7 feet. So as a miss distance, or magnitude of the range vector, we're looking at 24.7 feet. And this makes sense because cross range is initially 40,000 feet. And as time proceeds, that value decreases linearly, but the fluctuations of the pursuer and target separation in the altitude and downrange directions are on the order of 100 feet. So we really cannot see the range dynamics according to the pronav engagement here with this plot. So let's just isolate then range measured in the downrange and altitude directions where the maneuvers occur, and now we see something more interesting. The pronav is working to establish a collision triangle, responding to the target maneuver, and ultimately converging after a period of time to roughly about 20-something feet, where that continues until the final time, for this particular time constant of 1 second. Now let's look at how time constant affects the engagement kinematics. First, the time constant that's very small, 1/100th of a second. What we see is a more pronounced response of the pursuer to the weaving behavior of the target. At time to go 0, you can see the blue line just approach the red line, indicating a small miss distance. Now, if we increase that time constant in order of magnitude, what do we expect to happen? Everything looks pretty similar. At time to go 0, we see a small miss distance. This is consistent with 2D studies we've done for different time constants in previous modules. Now the example we've already looked at. Comparatively less oscillation in the pursuer as it attempts to respond to the target, and clearly a much greater miss distance for this maneuvering target. Now, what would you expect the pursuer behavior to be for a 10-second time constant? Notice the lack of response to the target motion. The pursuer does approach the target, but there is no weaving behavior that's introduced by the target motion in the pursuer trajectory. This is the pseudo-pilot response in each inertial direction for the time constant of 1/100th of a second. On each plot is the achieved and commanded acceleration of the pursuer. There's no observable difference between the commanded and achieved signal with a time constant of 1/100th of a second. Well, this is expected because essentially the pseudo-pilot is much faster than the commands of the guidance law. As expected, there's no acceleration in the cross-range direction up to time to go approaching 0, where we have that singularity in the pronav law in the denominator time to go squared. In the altitude direction, similar to the downrange direction, overlap of the achieve and commanded accelerations, indicating that the pseudo-pilot has ample bandwidth to achieve the desired acceleration command from the pronav law. Now let's compare this to a time constant of 1 second. Here we see the achieved acceleration has less amplitude and lags the commanded acceleration, indicating that the pronav command exceeds the bandwidth of the pseudopilot. Looking at the range to the target and the final milliseconds before time to go equals 0, we see the effect of the decreasing pseudopilot time constant on the miss distance, going from roughly 25 feet miss all the way down to 0.3 of a foot. Now the effect of changing the navigation gain. On the left-hand side, n equals 5. On the right, n equals 3. These are both for a time constant of 1/100th of a second. And what we see is that the larger navigation gain gives us a visually smaller miss. You can see space on this plot at TF, and at TF they're much closer together. Also, for an n equals 5, the pursuer spiraling in response to the target spiraling is more pronounced. Well, this is consistent with our expectations. In 2D analysis, we saw that the larger navigation gain gave larger accelerations early on in order to close the miss distance. Now again, range versus time and the final milliseconds before time to go equals 0. This is for a constant pseudopilot time constant of 1/10 of a second. And here's 4 different navigation gains where we see the decreasing trend in miss distance with increasing navigation gain. Here's a plot of downrange acceleration versus time over the full engagement, where acceleration commanded and achieved is shown for n equals 3 and n equals 5. Early on in the engagement, zooming in, we can see that the acceleration for n equals 5 is generally larger than for n equals 3. This becomes more apparent as time goes on until the very last moment. The commanded acceleration for n equals 5 becomes less than that for n equals 3. And then as time to go approaches 0, both commands experience singularities and the commands saturate according to the command limits of 966 feet per second squared, or 30 Gs. And while it's not as apparent here for this 3-dimensional example, comparing this case to the 2D accelerating target case we've previously looked at, the same trend is holding. The larger the navigation gain, the larger upfront acceleration that's required, but it pays dividends later on where a collision triangle is better established, and so less acceleration is required in the final moments of the engagement. Let's look at an animation of zero effort miss normal to the line of sight. This axis is in the altitude direction, this axis the cross range, and this one the downrange direction. Keep in mind that the target maneuvers in the downrange and altitude directions, and note also the scale of these axes compared to the cross range axis, which the target does not maneuver in. Just the maneuver plane of the target. Notice the zero effort miss value where we start is 0 in the altitude direction and non-zero in the downrange direction. To understand why zero effort miss in the downrange direction is initially non-zero, let's take a look at the initial engagement condition. The target has initial velocity in the downrange in cross-range direction, none in the altitude direction. The pursuer has its velocity vector aligned with the cross-range direction. So if it weren't for this small velocity component of the target in the downrange direction, the pursuer and target would initially be on a collision course. This small downrange component of velocity in the target is what's responsible for the zero effort miss being non-zero in the downrange direction initially. Now the pursuer proceeds along the spiral approaching the origin, but note that it stops just slightly offset from the origin itself. Now here's zooming in on the origin, where the final time to intercept, is this point right here. This distance from the origin is essentially the same value as the miss distance. So we have about 11.8 feet of miss in the downrange direction and about minus 21.7 feet of miss in the altitude direction. Reducing the autopilot time constant brings the spiral closer to the origin, indicating the reduction in miss distance. And now one order of magnitude less time constant, it appears to touch the origin. We can summarize the miss distance result with this plot of zero effort miss magnitude versus time. Here, 4 different time constants of the pseudo-pilot are shown, with a time constant of 10 and 1 second giving between 24 and 25 feet of miss, but then going down to 0.1 seconds, 1.7 feet of miss, and 1/100th of a second, 0.3 of a foot. Consistent with that spiral approaching the origin. Now I want to go back and interpret why we saw less weaving behavior in the pursuer as the time constant of the pseudo-pilot increased. Let's investigate with the 10-second time constant example. Here's its zero effort miss curve, where we see the initial zero effort miss spiraling into the origin. Now if we were to draw a vector from that origin to any point on that zero effort miss curve, we could say that essentially zero effort miss is decreasing as time to go decreases. And this is exactly what the pronav law is trying to do. It's trying to decrease the zero effort miss, hence establish a collision course so that the acceleration required by the pursuer is 0. Now recall that the target is weaving at 3 radians per second, or just about 1/2 of a hertz. So over the 10-second engagement, that means roughly 5 cycles. And if you count the total number of cycles in the zero effort miss plot, you see that you have about 5 cycles. So we're concluding then that the spiral in this zero effort miss plot is driven by the target maneuver frequency. Here's that zero effort miss plot again for the 10-second time constant. This is essentially what goes into our zero effort miss form of pronav. And then of course we have the G limiting, and that goes through the pseudo-pilot. And that's an important point right there. The pseudo-pilot, and in reality the autopilot, they act as low-pass filters. There's only a certain frequency content up to which they can respond to, and that's just dictated by the bandwidth of that autopilot or pseudo-pilot. So what we have here is frequency content in the pursuer acceleration with its origins in the zero effort miss that's being filtered by the pseudo-pilot. Then what we see coming out of that pseudo-pilot is less response of the pursuer because of the lower bandwidth that's prescribed by the 10-second pseudo-pilot time constant. This explains our observations earlier that as time constant increased, the pursuer responsiveness to the target maneuver was actually decreasing. To put it another way, the pursuer is more sluggish to target maneuvers. What we've seen from our exploration of this engagement is that the target weaving makes the pursuer weave. This makes sense because as the target weaves, the collision triangle is continuously adjusting so that the pursuer continuously has to make adjustments in order to establish that triangle according to the Pronav law. We saw that small values of time constants were necessary for small miss distance, but also that as we reduced the time constant of the pseudo-pilot, the pursuer behavior in response to the weaving target was exacerbated. That is, the pursuer weaved more in response to the target weaving. As the time constant increased, the weaving was filtered, but the miss distance was large. Plots of the zero-effort miss normal to the line of sight revealed some very interesting and beautiful patterns. We found that they were helpful for interpreting the engagement, and this included insight into the initial conditions, how Pronav was working, and ultimately at the time to intercept TF, what the miss distance resulted in. As we increased the navigation gain, the results seemed to follow a similar principle in 2D analysis for the constant accelerating target. We saw that as we increased n, it meant a minor increase in g's early on, but later less g's for intercept. And that intercept resulted in less miss distance as n increased. So these simulation results raise some practical questions about Pronav and how applicable it is for this type of a maneuvering target. As you can imagine, for a pursuer to take a less direct path to the target and weave in response to the target weave behavior, it's going to be using up a lot of energy in that process. And this is bad from a couple vantages. One is that as the pursuer maneuvers, it has to adjust its control effectors, and it's using a finite onboard energy supply to do this. So the more it maneuvers, the more likely it is to run out of energy to perform the intercept. But not only this, as the pursuer changes direction, the angle of attack and angle of side slip of that pursuer is also going to change. This introduces drag, which will slow the pursuer relative to the target. And as we know for Pronav, as the pursuer slows relative to the target, the intercept becomes more difficult. So in theory, yes, it's effective, but in practice, it's not the most energy efficient means. So while this simulation is illustrative of principles of Pronav, it's not to imply that this is the correct guidance for this target. Obviously, it's not the most efficient because we could conceive of more direct pathways to the target that would not be so responsive to the intermediate weaving of the target that would bleed off energy in our pursuer and lessen the likelihood of intercept. So as an improvement, we could possibly derive a guidance law that would leverage the known acceleration behavior or the known maneuver behavior of the target. And this has been done, and it works very well in this example. But the key thing is that we're assuming we know what that target will do, how it will maneuver. And when it comes to ensuring that we intercept the target, placing our bets on a presumed target maneuver can be a very risky thing. In this module, we've essentially performed a more in-depth investigation of an example from Paul Zarkan's book. This was Pronav in 3 spatial dimensions, Missile Guidance Fundamentals, Section 5, Module 2.